Now let us look at another example. This is integration of dx delta x square minus a square x square into x square. Now here fx is equal to x square and gx is equal to x square minus a square. So these are the two things. So what you will do is I will give you some hints. G is equal to x square minus a square, and that has to be 0. So that will be 0 at x is equal to plus minus a. Then and dg by dx, which is g dash represents dg by dx, and a dot dash represents integration of in space, dot over a function integrates integration in time. So g dot is dg by dt. Here it is only a function of x. So therefore g dash dg is equal to dg by dx is equal to 2x, which is equal to plus minus 2a at each point. So if you use that, the integration dx delta x square minus a square into x square is equal to summation over xi into xi, because for fx is equal to x square, so xi square fx exists only at the points where gx is equal to 0. Those are 2 points, so xi square divided by 2xi, that you can write as a square by 2a plus a square by 2a, that is equal to a. Now you know what does this imply. This implies that we can write delta x square minus a square and is equal to 1 by 2a into delta x minus a plus and delta x plus a, that you can see from the above integration. That you can see from the above integration. In the integration, what we have got, delta dx delta x square minus a square x square, that is equal to a square by 2a plus a square by 2a. So a square by 2a, past a square by 2a, 1 by 2a, take it common. Then what is left is delta, sorry, a square plus a square. When we will get a square into delta x minus a will give you integration of dx delta x minus a into a square is equal to a square. Similarly, integration of dx into delta x square plus a square is equal to a square. So from that we get that this is equal to 1 by 2a delta x minus a plus delta x plus a. Okay, next. The next example is again dx delta x square minus pi square cos x. So here we have different arguments x and x square. So we have to make them same. How t is equal to x square, let us use t is equal to x square, dx is equal to dt by 2 root t. So if we do that, now on the integration is from 1 to 4. Now when you do the change of variable t is equal to x square, then the integration becomes 1 to 16. So it will be 1 to 16 dt delta t minus pi square into cos x is now root over of t by r2 root rt, that is dt dx. For dx we have used dt by 2 root t, and for x we have used root t. So cos root t whole divided by 2 root t. Now if you integrate that back, that will give us 1 by 2 into root pi minus 1 by 2 root pi. This integration will give us minus 1 by 2 root pi. Integration from 1 to 16 dt delta t minus pi square cos root t into 2 by 2 root t. That will give us minus 1 by 2 root pi. It is simple because it is in the form delta rt minus pi square cos root t by root t. That is what you are going to integrate. So it is of the form delta x minus a into cos a by cos x by x. Fx is equal to cos x by x. So use that. So integration will be cos pi square by pi square. So from that root t will give you pi. So from that you will get root pi. Numerator will give you 1. Okay. Now up to this point, we have discussed about the Dirac delta function in one dimension. So we consider only x. Now this function can also be in 2D or 3D. So in Cartesian coordinate system in 3D, we can use a product of delta functions for each dimension to construct a 3D delta function. So if you want a 3D delta function, take the product of delta function in each dimension. So delta small x vector minus capital X vector. So capital X is the particular value, small x is the variable. Delta small x vector minus capital X vector is equal to delta x1 minus capital X1 into delta x2 minus capital X2 into delta x3 minus capital X3. This is the definition of Dirac delta function in 3D. So that implies that if I integrate over dx1, dx2, dx3 on the 3 dimensions, well, here you can take x1 is equal to x, x2 is equal to y, x3 is equal to z. That way also you can take, but for generality we are writing dx1, dx2, dx3. So if you have an n-dimensional space, so then this will be up to dxn, and that is why we are writing like this. So integration dx1, dx2, dx3. There we are integrating over dx only. In the one dimensional, in 3 dimensional it is dx1, dx2, dx3 into delta x vector minus capital X vector fx vector. That will be dqx, which is in dqx. When we write this way, dqx, that indicates the volume integral. dv, instead of writing dv, in physics people usually write dqx. Rarely we use dv, but mostly in physics notation it is dqx. So integration of dqx, and dqx means dx1 into dx2 into dx3, or that you can write as dx dy into dz. So that is what is dqx. So integration dqx delta small x vector minus capital X vector. So that into f is any arbitrary function, capital small x vector. So that with the analogy with the 1D Dirac delta function, so that will be equal to f of capital X. So small x minus capital X is equal to 0. That is where it exists, and the value becomes function of capital X. So this is for the integration. Now in spherical or cylindrical coordinate system, instead of Cartesian coordinate system, if you are using spherical or cylindrical coordinate system, then the singularity in the function delta r will occur at r is equal to 0. Singularity means where it becomes infinity. So singularity in the function delta r becomes r, that occurs at, for which value of r it will be singular? It will be singular for the value when r is equal to 0, mod of r is equal to 0. Theta and phi, that you know in cylindrical coordinate system or spherical coordinate system, theta and phi are undefined at origin. At origin they are singular, they are not defined. So away from the origin you can define an angle, but exactly at the origin you can define an angle because there is no angle there. Now to obtain integration dqx delta x, that is equal to 1. So on dqx delta x in 3 dimension, that you can write as integration on 0 to infinity r square dr. For dqx you can write this way. dqx is equal to r square dr, then d phi, then sine theta d theta. So sine theta d theta is d cos theta. So 0 to infinity r square dr minus 1 to 1 d cos theta integration 0 to 2 pi d phi into delta x. Now that if we evaluate what we are going to get, let us see. Delta x must have a factor of 1 r square, and this r square cancels on the r square in the volume element. So this r square will cancel out in the volume element. R square dr d theta d phi. So that r square will cancel out with the factor 1 by r square of delta x. Then delta x must be isotropic, which means it is same everywhere. For every value of theta it is same, so every value of phi is equal to same. It is same at a distance r. Then it depends only on the radial component or radial coordinate r. Delta x must have these three properties. Now let us write delta x is equal to, in terms of these three properties, let us write delta x is equal to A. A is an amplitude, is a normalizing factor. So amplitude A into delta R into 1 by R square. Okay. And if we write that way, A is the normalizing factor, which is reciprocal to the integral over the irrelevant coordinates. Irrelevant coordinates are theta and phi. So A inverse 1 by A is equal to integration minus 1 to 1 d cos theta, then integration 0 to 2 pi d phi. So d cos theta integration minus 1 to 1, that will give you 1. That will give you 2. Then integration 0 to 2 pi d phi, that will give you 2 pi. So this will be 4 pi. So A inverse is equal to 4 pi, or delta x is equal to 1 by 4 pi r square into delta r, or delta x in 3D is equal to 1 by 4 pi r square delta r. So what is important is, remember, in 3D delta x is equal to 1 by 4 pi r square delta r. Derivation is not important. Important is this 1 by 4 pi r square delta r. This is what is important. This is what we are going to use. Okay. Similarly, in cylindrical coordinate system, phi is irrelevant. So delta function for the origin will be delta x is equal to 1 by 2 pi r delta z. Because we will have variation along r and variation along z, it will be 1 by 2 pi r delta z. So remember this. Some applications is in electrodynamics that we are going to study is collection of point charges as charge density, because point charges are separate, they are not continuous distribution. So that is one important point. Construction of surface and linear charge density. These are some of the applications that we are going to deal later. Just remember these two things. Now we'll come to what is called field. We are going to deal with electric field and magnetic field or electromagnetic field. By definition, field is a type of observable. So if there is an observable, there is an entity which can be observed, then that is called a field. And let us look at an example of a field. Consider the wind speed, a speed of wind. Let us take that as v. V is the speed of wind. Now, if the speed of wind, my question is it same near the seashore and at Vanjavihar, at the university campus, or if you come to the town, Berhampur town, you will see that the speed is different. When you observe the speed of wind near the sea, it will be more. As you come to the town, as you come to Berhampur University, it will be different, it will be less. As you come to town, as you go away from seashore, it will keep on decreasing. Right. Is it the same, whether the wind speed is same in summer and winter at the same place? Suppose you are considering the seashore. At the seashore, in the summer, whatever is the speed, Will that be the same speed in the winter? Will that be the same speed in the autumn? The speed will be different. So at different times, the speed will be different. At different points, at different locations, the speed will be different. What you are observing is the speed. Speed is the observable. The observable is dependent on time and dependent on space. So you observe it at time and space. So these two questions that I asked, the answer is negative to these two questions, which means it is determined by where it is measured and when it is measured. And the observable is determined by, or the field is determined by where the observable is measured and where it is, when it is measured. When and where, these are the two important things for on the observables. Wind speed, from this we can say wind speed is a function of position and time. Similarly, you can talk about temperature. Temperature near a stove and temperature away from the stove. They are different and at different times. So if you change the time, so if there is less fuel, with time fuel consumption will be there. So fuel will reduce, temperature will reduce as you go away. So where you are measuring, as you go away from the stove, temperature will be less. As time increases, fuel reduces, temperature will be less. So that is another thing, another example. So therefore, we define the field as a type of observable. So it is a type of observable which is characterized by a number determined from when and where it is observed or measured. This is how you define field. Field is a type of observable characterized by a number determined, and the number is determined from when you have measured the observable and where you have measured the observable. These two things, when you are measuring it, where you are measuring it, that characterizes the number or that determines the number, and the number characterizes the field. So field is a type of observable characterized by a number determined from when and where it is observed or measured. So this is basic definition of field. We understood what is field. After this, we will start working on field from the next class onward. So we'll stop at this point for today. If you have any doubts or questions, you can ask me. I have already mailed you the notes. You can see the notes. So, tole 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 somba tole tapakota stops streaming.